Today we're going to talk about carboxylic acids. Now, a carboxylic acid is within the carbonyl family in that you can see it has a carbonyl carbon to which a hydroxyl group is attached. Now, this entire functional group is called a carboxyl, and it's the hallmark of carboxylic acids. Of course, you have an R group which can represent any alkyl or aryl. So let's talk a little bit about nomenclature. And as expected, the nomenclature for carboxylic acids, as is the case with most of the compounds we've observed, depends on the longest continuous chain of carbons, in this case bearing the carboxyl group. So if you look at my examples, I have a 1 carbon, 2 carbon, 3 carbon, and 4 carbon carboxylic acid. Now, if we look at the 1 carbon, if I compare this to a 1 carbon alkane, which of course is methane, I would drop the final E from methane and add the suffix oic. So methane becomes methanoic, and we tack on the word acid. So methanoic acid. A 2 carbon carboxylic acid would become ethanoic acid, where we drop the final E from ethane and again add the OIC suffix. Following suit, we would expect a 3 carbon carboxylic acid and a 4 carbon carboxylic acid to be propanoic and butanoic, respectively. Now, when we discussed aldehydes and ketones not too long ago, we observed that many of them have common or trade names. Carboxylic acids are no different. So we would call a 1 carbon carboxylic acid formic acid, a 2 carbon acetic acid, 3 carbon propionic, and 4 carbon butyric. One of the questions that often comes up with carboxylic acids is, are they real acids, at least within the context of what we think of when we hear acid? And the answer is yes, absolutely. Carboxylic acids are classified generally as weak acids, but they do have an ionizable proton, what we would call an acidic proton. And when they dissociate, they also release a conjugate base, which we will call a carboxylate. Now, again, they are weak acids. In general, the pKa value for carboxylic acids is around 5. And surprisingly, the number of carbons within the R group really doesn't have much bearing on the acidity of the carboxylic acid. Now, we can increase the acidity if we add an electronegative substituent to the carboxylic acid, particularly if we add it to the alpha carbon or the carbon adjacent to the carboxyl. For example, here we have acetic acid. Now, we know that acetic acid dissociates into a proton, and the carboxylate also known as acetate, that's the conjugate base. And if we look at the dissociation for acetic acid, the Ka value is about 1.8 times 10 to the minus 5, or a 4.7 pKa. If we now attach fluorine, which we know is pretty electronegative, to the acetic acid, notice that the Ka for the dissociation of fluoroacetic acid has increased to 2.5 times 10 to the minus 3, which is approximately a 100-fold increase. Let's talk a little bit now about how to make a carboxylic acid. And we're going to look at some of the more common methods and maybe some of the lesser common methods. So we've already seen from previous discussions that oxidation is pretty big when it comes to making carboxylic acids. In fact, we know that if we take a primary alcohol and treat it with a strong oxidizing agent such as permanganate, chromates, dichromates, we'll oxidize that alcohol directly to a carboxylic acid. So for example, if I have something like N-propanol and I treat it with permanganate, I'll get propanoic acid. Alcohols are not the only potential source of carboxylic acid. We can also oxidize aldehydes. Now, if you recall, we could also take a primary alcohol and oxidize it to an aldehyde. The only difference here is the strength of the oxidizing agent. To make an aldehyde, if you recall, we would use a lesser oxidizing agent such as pyridinium chlorochromate or pyridinium dichromate to get the aldehyde. All we're doing is continuing the oxidative process. So if we take our aldehyde and treat it with the same strong oxidizing agents that we used with the primary alcohol, then we can go straight to a carboxylic acid from the aldehyde. Alkyl benzenes. During our earlier discussion on arenes and aromaticity, we made the observation that if a benzene ring has any alkyl group attached, treating it with a strong oxidizing agent will convert that alkyl benzene directly to benzoic acid. So if, for example, I had toluene and again treated it with something like permanganate, I'd go straight to benzoic acid. Now, bet you didn't think that you would see Grignard reagents in this discussion. We know from past experience that a Grignard in conjunction with formaldehyde will give you a primary alcohol, a aldehyde in general, will give you a secondary alcohol, and a ketone will give you a tertiary. But did you know that Grignards can also be treated with plain old carbon dioxide and then hydrolyzed to form a carboxylic acid? If you look at the basic mechanism, the reaction between Grignards and CO2 is really not that much different from a aldehyde or ketone. The Grignard, in this case, acts as a nucleophile towards carbon dioxide, and we form this halo magnesium carboxylate complex, which will in turn be hydrolyzed to give us our carboxylic acid. So, let's say I have 2-chlorobutane and I make a Grignard out of it. So I treat it with magnesium and diethyl ether, and here I have my Grignard. If I then treat this with carbon dioxide and hydrolyze it, I will get 2-methylbutanoic acid. Well, that pretty much covers everything that I wanted to say in terms of nomenclature, identification, and synthesis of carboxylic acids. Our next discussion, and I hope you'll join me, will involve some of the more common reactions that carboxylic acids undergo. Thank you for your attention, and I look forward to seeing you soon.